If you can't see the slides, I think we can probably fit one more person in that far back corner there. And you guys maybe, I had this idea that maybe you could like stand right there, or maybe in that corner we can fit. I'm not sure we can fit you guys though, I'm sorry. Okay, so I'll start. Please feel free to try to find a place to sit. So I work for MongoDB, and it's a database, and we make drivers for the database in lots of different languages, like in C# and Java and Haskell and Ruby. You name it, we have a driver for it. And once upon a time, somebody benchmarked two of our drivers against each other. And this person wrote a blog post with the following title: MongoDB Facts, over 80,000 inserts per second on commodity hardware. So this guy, not somebody that I know, but his name is Vlad, and he had written a benchmark that compared Node.js to Python and their performance using MongoDB. And his blog post had good news and bad news as far as I was concerned. So the good news is he got 88,000 inserts per second using Node.js and MongoDB on his laptop. So that's pretty impressive. Yep. The bad news is that he compared it to Python, and he got less than a third of the performance. Now, which of these two drivers do you think is my code? So his conclusion was PyMongo is slower than Node.js. The first that I heard about this was when I got the following email from my boss. So Steve is my boss, and he's writing me to ask, hey Jesse, why is PyMongo so damn slow? And he's CCing Elliot, who is his boss. And Elliot is the CTO of MongoDB. He is the main writer of MongoDB. He is one of the best programmers I know, and also one of the most short-tempered. So I was on high alert. I needed to answer this question. My top priority is to know why, and my next highest priority was not to look like an idiot in front of Elliot. So I turned to the actual benchmark code. So this is what Vlad wrote, and it starts off pretty straightforward. It imports PyMongo. It gets a handle to a database within the MongoDB server. It gets the handle to a collection within the database, and it clears all the documents so that it always has a fresh start. No problem. Let's move along. So what does Vlad do next? He wants to insert 80,000 documents, and he wants to do it 5,000 documents at a time. So far so good. MongoDB works best when you insert in large batches rather than one at a time. So the problem that I'm looking for, it's not here yet. So I'm going to keep looking at his code and try to find the problem. And here's where things start to get a little bit weird. Why is he importing random? What's he going to do with this? And then what happens next? What is he doing with datetime? He makes a date that's the beginning of 2012, and he makes another date that's the beginning of 2013. And then he counts the number of seconds between them and assigns that to delta. What the heck is this about? Well, we'll find out in a minute, because we're going to look at the main loop of the benchmark. So this is a lot of code. You don't need to read it right now, because we'll step through it bit by bit, especially because I have a laser pointer. So to begin with, he just does for I in range 0 to 80,000. No problem. But the next three lines are kind of crazy, and we need to decode this bit by bit. So we'll start with the time tuple thing there. He's just converting the year 2012 from a datetime to a time tuple, And then he uses makeTime to convert that from the time tuple to a timestamp. Then on the next line, he makes a random number between 0 and delta. So remember that delta is the number of seconds in the year 2012. So he's just making a random number somewhere between 0 and that. By adding that to the timestamp for 2012, he's now created a random number evenly distributed over the range of 2012. And then finally, he converts that timestamp back to a date. So now he has a random date in 2012. Fantastic. The next line, he just makes some random value, and then he sticks it into a document and adds the document to his batch. Whenever the batch reaches the desired batch size, he inserts it, and then he resets the batch. And he does that until he's inserted 80,000 documents. All right, great, easy enough. How does his benchmark end? He measures the time it took. He divides 80,000 by that, and he gets about 30,000. And when I run this benchmark on my laptop, I get about 30,000 too. So far, so good. I can reproduce his results. Why is this so much slower than the node code? So I'm not going to show you the node code, because this is a Python conference. But suffice to say that it does the same stuff. It inserts 80,000 documents, 5,000 at a time. Each document has a random date and a random value. There's no differences between the two code samples that can explain the difference in performance. So now I'm a little bit stumped. What do I say to Steve and Elliot about why PyMongo is so slow? Well, it's time to pull out a profiler. And why do I turn to a profiler to answer this question? Well, sorry, the question, right, fine. Why do I pull out a profiler? And it's because debugging, optimization is sort of like debugging. You want to apply the scientific method when you're optimizing, just the same as you want to apply the scientific method when you're debugging. And the scientific method goes, you come up with hypotheses, and then you test them by performing experiments. So when you're optimizing, the hypotheses that you come up with are like, if I change this code in the following way, that'll make my code faster. And if you want to get even more precise, you could say, changing this code in the following way will make my code up to 20% faster or up to 30% faster. And once you've come up with that hypothesis, you need to test it, so you rerun your benchmark and you see if you were right. And you repeat this process until either your code has hit the desired target or you get tired. Where in here does profiling come in? The profiler helps you come up with hypotheses. It helps you come up with ideas for places to change your code, because it tells you where your code might be spending most of its time. The profiler can't tell you how to change your code. It can help you estimate how much savings is possible. But it's only a hypothesis. Your profiler doesn't tell you anything for sure. Only your benchmark can actually be a valid experiment. So I've decided to use a profiler to come up with hypotheses about why this benchmark is slow. Which profiler should I use? So everybody knows about cProfile, right? All of the talks are about cProfile. It comes in the standard library. It has C, so it must be fast, right? cProfile is very limited. For one thing, it doesn't understand gEvent or any other Greenlet-based application framework. So I wrote a thing called GreenletProfiler, which does the same. So you should know about that the next time you're faced with that problem. But in this particular case, the benchmark is not using Greenlets. So GreenletProfiler is not the right tool. The tool that I used was Yappi, which is yet another Python profiling implementation. And it's written by this very talented Turkish programmer named Sumer Sip, who is a great programmer and not very good at naming things. Compared to C profile, Yappi is just as fast because it's implemented in C, and it measures the same thing. So neither of them is a line profiler. They both measure the execution time of whole functions. Unlike C profile, Yappi it can measure either either wall clock time, which is what C profile measures, but it can also measure CPU time, which is basically the instruction count that a given function cost over the course of the entire program's execution. So C profile can be fooled if your function sleeps for 10 seconds. C profile will say, wow, that function took 10 seconds to execute, whereas Yappi understands that that's not an actual cost in terms of CPU time. Yappi can also profile all of the threads in your interpreter, whereas C profile can only profile one thread. And Yappi can export to call grind, which we'll see in a minute why that's a really useful format to store your profile information in. So first of all, we want to see how to actually use Yappi. So I updated Vlad's benchmark code here to first import Yappi. I set the clock type to CPU because I'm interested in only the time that's actually spent in the benchmark, not the time that MongoDB takes to do the inserts. And I tell Yappi to profile built-ins because I'm curious whether Yappi might tell me that like rounding numbers or converting between one time format or another is very expensive. So turning built-ins on means that I can profile functions that were implemented in C as well as functions that were implemented in Python. So I have Yappi started up, and then I run just the regular benchmark code. So I in range 0 to 80,000 and so on. And down at the bottom, once the profile is finished, I get the function stats from Yappi, and I export them in call grind format. So what do I do now that I have this profile information? I need to investigate it somehow. I need to visualize it so that I can start to answer this question, why is PyMongo so damn slow? So there's this great Linux tool called kcachegrind. It can read call grind output, which is why having Yappi output to call grind is so useful. And I know that this is like a lot of multicolored output and it looks crazy, but the main thing to look at here is that the functions are sorted by the amount of time that each one cost inclusively as a percentage of the program's total running time. So the top there, collection.insert, takes 2/3 of the time, and that's sort of what you'd expect, right? Most of the time that the benchmark takes is spent inserting things into MongoDB. But what's nice is that we can already form a hypothesis based on that piece of data. We can say, no matter how much I optimize PyMongo, I can only remove 2/3 of the total running time. So that means that this benchmark can only ever be 3 times faster by optimizing PyMongo. So even if PyMongo were infinitely fast and took 0 time, this benchmark would only run as fast as the node benchmark, not faster. So that basically tells me that it's not my fault. Even if I were just incredibly brilliant and a much better programmer than I am and made PyMongo incredibly fast, I probably still couldn't beat the node benchmark. Node is just faster than Python. Sorry, it's a JIT, and it's written by Google. V8 is at least. So it's hopeless, right? But there is sort of another interesting thing that we can learn from this, which is that a lot of the time is spent in all of this other stuff. It's Date time manipulation and round is surprisingly expensive. It takes up more than 5% of the total runtime. So based on that information, let's go back to the benchmark code. So here's that crazy part that we were looking at before. That's where make time and time tuple and round, that's where all of those things are getting called. And we can hypothesize that, all told, that takes a third of the runtime. That's the sum of all of that stuff. It's about 35%. So what if we just replaced it with datetime.now? We would expect our code to be about 30% faster. So having formed that hypothesis, we now run the experiment. So we rerun the benchmark. And it actually turns out quite a bit better than we'd hoped for, right? We'd been hoping for a 1/3 improvement, and we get something more like 40% better. So we're still not at 88,000 inserts per second, and we already knew that we probably will never get there. But we can get substantially closer just by replacing Vlad's very complex datetime manipulation with something very simple. So, whoopee, I take this back to Steve and Elliot, and I can sleep soundly at night. So the sort of takeaways here are that profiling helps you generate hypotheses, but it can never tell you anything for sure. You need to run your benchmarks. And also that profiling helps you to estimate what savings are possible by optimizing a given piece of code. But I don't know, are you totally satisfied? If you're anything like me, you can't really sleep soundly until you understand how something works under the hood. So in the next 3 minutes, let's write a profiler. How do profilers work? So they're written in C, and they're based upon a callback which has to have the following C function signature. So they take 3 arguments. The first is the frame object. So this is a data type within CPython, the Python interpreter. The second argument is what. What happened? Was it a function call or did a function return? And the final argument is usually blank, but if what is a function returning, then that argument is the return value. So I don't actually understand what that's useful for, but your profiler will be told what the return value is. So when a profiler starts, it calls the following Python C API function, and it passes the callback's function pointer in to tell the interpreter to execute this callback whenever a profile event happens, whenever a function starts or completes. And the next thing we're going to look at is the heart of the CPython interpreter itself. So here it is, the famous, the invincible PyEval frame X. This is a 2,000 line function written in C, and this is where Python actually interprets bytecode. Eval frame X is where it says what bytecode am I interpreting and what should I do about it. And that's the only place in the whole interpreter that bytecode actually gets turned into action. It's kind of fun to read. You should go look at it. It's in ceval.c. But we're not going to look at the bytecode interpreter today. What we're looking at is just the entrance and exit of eval frame X. So notice that at the entrance, it takes a look at this tstate object. Tstate is a global variable. It's the state of the current running thread. And since Python has a global interpreter lock, the current running thread, well, there's only ever one of them. The interpreter then checks whether a profile function has been registered, and if so, it executes it, and it tells it, here's the frame, the what argument is call, that's the thing that's happening, and the third argument is none. And then whenever eval_framex finishes executing a function, it comes down here and it calls the profile function again, and it tells it we're still in the same stack frame, but this time the thing that's happening is a function call return, and there's the return value. So the last thing we need to look at to see how profiling actually works is how would you implement that callback function? So here's sort of a sketch of that. Remember, it takes the three arguments, the frame, the thing that happened, and the return value, if any. So it would just be a big switch statement. And it would switch over the what value. So if what is a function call, then it would take the frame object and it would get the current executing code object from the frame. So this would be the currently executing Python function. And then what we probably want is like the file name and the function name of whatever function is being called right now. So we would get that off of the code object, and then you'd probably record the fact that this function was executing in some data structure. Maybe you'd write down what time it had been called so that you can then figure out the duration. Right, you can sort of see how, given this basic building block, you could implement a Python performance profiler for yourself. So that's what I have to say. We have about 3 minutes for questions, so fire away. Yes? What is the overhead introduced by the profiler? It's a good question. On this benchmark, when I ran it with Yappi turned on, it was about twice as slow. And in the realm of profilers, that's actually very, very good. Generally speaking, since a profiler has to execute multiple function calls to record the fact that each function call has happened once, they can add overheads of as much as 10 or 20 times the total runtime. And this is one of the reasons why profiling only allows you to form hypotheses, right? It doesn't actually allow you to prove anything because there's sort of a Heisenberg thing going on here. Profiling code makes the code slow. So if you're trying to figure out why it's slow, you have to turn the profiler off in order to actually estimate how it's performing. So you can get some idea, but you need to turn the profiler back off and rerun your benchmark to find out what's really going on. Are there other questions? All right, this is a hot room, so I am going to let you all go. Thank you very much.